So let me introduce the second speaker for this session on solar and radiation energy conversion is Professor Shanhui Fan. Shanhui Fan is a professor of electrical engineering and the director of the Edward Ginston Laboratory at Stanford University. He is a principal investigator on the GCEP efforts high-efficient thin-film solar cells using nanoscale light management and nighttime radiative cooling, harvesting the darkness of the universe. That will be the title of his talk. His research interests are in fundamental studies of solid-state and the photonic structures and the devices, especially photonic crystals, plasmonic and metamaterials, and applications of those materials in energy and information technology. Fan is a recipient of NSF Career Award, a David Luca Pickard Fellowship in Science and Energy, the National Academy of Science Award for Initiative in Research, and Adolph Loeb Medal from the Optical Society of America. And Fan earned his PhD in theoretical condensed matter physics from MIT. So thank you and welcome.
Well, thank you. So I'd like to talk about some of our work, a slightly broader perspective of some of our work in trying to do radiative cooling. So as way of a background, we're talking about renewable energy resource here. And so it will be interesting to examine the basic thermodynamic resource that's available to us. Certainly, there's the sun, and Professor Zheng talked about, which is a fantastic energy source. On the other hand, if you just go out and look away from the sun, and if you imagine that the sun is not there, then you should see the dark universe. And the universe is extremely cold. This is at a temperature of 3 Kelvin. Now, from a basic thermodynamic point of view, something that's cold is also extremely important as well. If you think about just the Carnot efficiency conversion limit, it certainly will be great if all the energy conversion process that's currently going on do not use the Earth as the heat sink, but use the universe itself. So what we would like to do here is to point out a pathway towards harvesting this thermodynamic resource that really has not been very widely discussed. Now, one of the very important points about photonics that we all pursue here is that it provides remote wireless access to thermodynamic resource. None of us doing solar cell research actually sit in the sun. So by the same token, you actually do not be sitting in outer space to benefit from the existence of it. And the black curve here is the measured transmission spectrum in Hawaii, actually, of the atmosphere. It's a fairly complicated spectrum, but I'd like to draw your attention to the wavelength range between 8 to 13 micron. And that wavelength range here, the atmosphere is very transparent. And that happened to be at the peak of the black body radiation spectrum for a black body at 300 Kelvin. So another way of saying it is that if you step outside, you are actually radiating heat into outer space, every one of us. And so that's a mechanism that potentially can be used for cooling purposes. And in fact, there has been a technology that's been around called nighttime radiated cooling in precisely trying to do this. And what they do is they take a black radiator, anything that looks black, like a carbon black radiator would do. You bring it on the roof at night, have it face the sky, surrounded by an insulating material. Now the heat is going to be radiated into the sky, and therefore the radiator will have a lower temperature. It is actually a fairly straightforward experiment, and we could do that easily here at Stanford to show that in doing so, you can get a temperature about 10 to 15 degrees Celsius below ambient. This is a technology that has been around actually for a long time. Some of the early papers date back to even the 60s. But what we are seeing is a very important opportunity that have not been addressed, where one can use photonic technique and concept to drastically improve the performance and widen the range of application that you can think of with this kind of radiated cooling concept. So in this talk, I'm going to talk about three separate things. I'm going to talk about our work on daytime radiative cooling. We're then going to show how to combine radiative cooling with solar cell. And finally, I'm going to talk about some of the latest results that we have in the GCEP project, where part of the project was to try to push the limit of nighttime radiative cooling. So let me start with the daytime radiative cooling. The experiment that I showed you was carried out at night. Now, if you care about cooling, of course, you would like to do it when the day is hotter. And that's probably around now when the sun is shining. You probably would not imagine to put a piece of black carbon and go up to the roof right now to see any cooling. And the reason, of course, is a very simple one. The sunlight heated up. So with that notion, then the concept for daytime radiative cooling actually is a fairly straightforward one. What you would need to imagine is a structure that has an emissivity or absorptivity spectrum that looks like this, that it reflects all the sunlight so that it doesn't get heated up by the sun, but it strongly emits in the 8 to 13 micron window. And remarkably, that kind of structure has never been constructed before. So together with Ashwas Raman and Lin Xiaozhu, who is reflected in this mirror here, and that's our sample, we constructed one of these samples on an 8-inch silicon wafer. The structure consists of 7 dielectric layers sitting on top of silver. And these dielectric are made of hafnium oxide and silicon dioxide, with silicon dioxide, your common glass, being the primary ingredient. The top 3 layers have thickness on the order of hundreds of nanometers for radiation purposes, and the lower 4 layer has thickness of tenths of nanometer for reflection purposes together with silver. So if you measure the spectrum, it has a very strong solar reflectivity on the order of 97% average over the entire solar spectrum. On the other hand, it has an emission peak that's right in the 8 to 13 micron window. So we then bring this up on the roof, and this is the roof of our electrical engineering building at Stanford. So it has a flat roof, which is very nice for us. And we build the apparatus to house the photonic radiative cooler. The key point, without going into detail here, is to recognize that roof is a very hot place. And so in order to be able to do cooling on the roof, the thermal design actually is extremely important, and that we struggle quite a bit with it. But eventually, that's what we come out. So the green curve here is the solar irradiance, and it has a peak of about 900 watt per meter square hitting the sample. The black curve here is the ambient air temperature, and the blue curve here is the photonic radiated cooler temperature measured. And you can see a 5 degrees Celsius difference between the ambient air temperature and the photonic radiated cooler temperature right at the peak sunlight of 900 watt per meter square. So without using any electricity, and this is a purely passive approach, we may nevertheless generate a temperature that's significantly below ambient air. And that opened the possibility of thinking about drastically reducing the electricity consumption for air conditioning. The US actually, 15% of the building energy consumption goes into air conditioning. So being able to scale this up would be actually quite important. And that's a project that we're undertaking. This is artistic rendering, this is not real, of what the system would look like. So it would be many meters square of panel with a water loop underneath it, and to provide cold water that then can be used to drive, to reduce the electricity bill for a water-chilled air conditioning system. And that actually, we are processing of realizing it, but I'm showing this picture just to point out that in many ways, in terms of form factor, this looks very much like either the solar cell or the solar thermal hot water system. But in this case, we're of course running it for a completely different purpose. So up to this point, we are constructing a structure for cooling purposes where we get rid of all the sunlight. So we're not using any of the sunlight. On the other hand, it would be great if you can combine radiative cooling with the utilization of sunlight. There are many potential application for this. You can imagine a situation where you like to cool down your car under the sun without influencing the color of your car, for example. But here, being an audience for solar cell, I'm going to specifically talking about trying to cool down solar cells. So as I hope to show you already experimentally, roof is a very hot place, and the solar cell sits on the roof. It faces the sun, and therefore its temperature gets quite high. Typical rooftop silicon cell operates at a temperature of about 50 to 55 degrees Celsius. This has very severe consequence on the operation of the solar cell. The efficiency actually goes down as the cell gets hotter, and the lifetime also goes down very significantly. So it influences both efficiency and the cost. So it would be great if there's a passive way to cool down the solar cell. Now, by definition, a solar cell sits and faces the sun, and therefore it faces the sky. And so it will be very natural to think about radiative cooling of solar cell as well. If you look at the emissivity spectrum of a silicon, this is a typical emissivity spectrum. It has very good absorption, as you would expect, in the shorter wavelength side, above 1.1 micron or so, and that's what you use solar cell for. On the other hand, it has relatively little thermal radiation that you can use. So consequently, a silicon, in fact, is not a very good very good radiative cooling material. In order to improve its radiative cooling capability, what you would like to do theoretically is to imagine a structure that has an emissivity spectrum that looks like this. It will have the same emissivity spectrum as silicon. So you put something on top of silicon without affecting the solar absorptivity, but you drastically boost the emissivity on the 8 to 13 micron window. And in order to do that, we perform the following experiment. So we compare 3 samples. The first sample is a bare silicon structure, and this is a 525 micron thick silicon with a 75 nanometer silicon nitride layer, and with a back mirror. This is a wafer that people usually use as a starting point for constructing a solar cell. What we then do is to compare the performance of this cell, this structure, the solar absorber, with 2 other structures where we keep the silicon part to be the same, but we put additional layer on top of it. In one case, we put a 500 micron thick silica layer, and in the other case, we put a 500 micron silica layer with a photonic crystal. So what we do is we use photolithography and introduce a periodic array of air holes into the silica layer. The periodicity here is about 6 micron because we're trying to control thermal radiation here, which have the long wavelengths. We then compare the optical and thermal properties of these 3 structures. So these are the spectrum, the absorption spectrum of the 3 structures, both on the solar side as well as on the thermal side. On the solar side, in the short wavelengths, visible and near infrared, the 3 structure actually has very similar absorption characteristic. In fact, the photonic crystal structure with silicas with holes actually have slightly higher solar absorption compared with the other structures that we have there by about a few percent. On the other hand, the thermal side of the spectra are very different. The black curve is the silicon thermal radiation spectrum. As I mentioned, it has very little thermal radiation, relatively speaking. The blue curve here is the absorption spectra of the thick uniform silica layer. It has a greatly enhanced absorption, but because there is an impedance mismatch between silica and air, there's actually a strong reflection as well, and consequently, there's actually a very large dip in the emissivity right in the transparency window of 8 to 13 microns. So a thick piece of silica is actually suboptimum as far as radiative cooling is concerned. The red curve here shows the photonic crystal sample. In this case, it has near unity emissivity over the entire far infrared wavelength range. And so what we have constructed here with the photonic crystal actually is a visibly transparent black body, which is a somewhat unusual concept if you think about what your mental image of what a black body should look like. So we then do the rooftop experiment where we compare these samples. So in this case, we tilt the sample to face the sun so that they're about close to 1,000 watt per meter square sunlight hitting the structure. And both the planar silica structure and the photonic crystal structure has much lower temperature compared with the bare silicon structure. The temperature difference here can be as large as 13 degrees Celsius. This is an experiment where we're really trying to prove the fundamental potential here. So we cut down the convection by using a polyethylene film to cover the surface of the apparatus. On the other hand, in this particular case, because the sample temperature is higher than the ambient, one can actually combine radiative cooling with more conventional one, for example, with convective cooling. So to demonstrate that, as a simple experiment, we just take off the polyethylene film as a cover. And as we do that, the temperature gets a lot more noisy because the wind blows through the sample, so the temperature fluctuates a lot more. But nevertheless, you still see very significant temperature reduction comparing the photonic crystal sample with the bare sample. In this case, the average is about 5 degrees Celsius. A temperature difference of about 5 to 10 degrees Celsius actually can be rather significant. A 10-degree Celsius temperature drop, for example, would translate into approximately a percentage point improvement in silicon solar cell. So we do think that there is actually very interesting potential through this demonstration of combining the utilization of sunlight with the manipulation of thermal radiation. So in the very last part of my talk, I'm going to report on some of the new projects that we've been undertaking with the support of GCEP, and that's to re-examine the nighttime radiative cooling. But in this case, to push to the limit and to look for the possibility for harvesting power at night. So I would like to show you some of the latest results where we're trying to push the limit of nighttime radiative cooling. Again, we start with the state-of-the-art, and the state-of-the-art has a temperature difference, temperature reduction of about 10 to 15 degrees Celsius at night. And this is usually accomplished by using a black emitter, a standard black body as an emitter, like a carbon black. Now, it is important to realize that even at night, a black body emitter is not ideal for radiative cooling purposes. So the blue curve here is the simulated transmission spectrum of the atmosphere at Stanford. So it's right here. And it basically, again, has a high transmission window of 8 to 13 micron, not as high as where Hawaii is, but still a very high one. If you imagine that you have a black body radiator, that black body would radiate outside in the 8 to 13, radiate heat outside of the Earth in the 8 to 13 micron window, which is great for cooling purposes. On the other hand, in the wavelength range where the atmosphere is not transparent, for example, somewhere around 6 micron, the radiator in this case behaves as absorber and absorbs downward radiation from the atmosphere. And that will be a heating purpose. That will be a heating mechanism. So consequently, even at night, if you would like to get to high-performing structure, you would like to go beyond what people have traditionally used for cooling purposes in terms of using a black body emitter. And instead, you would like to have an emitter that looks like this, which essentially has very high emissivity in the 8 to 13 micron window, but almost nowhere else. And this, if you look at theoretically, indeed can give you very large performance gain. And this is assuming an ambient temperature of 20 degrees Celsius at night, a transmission spectrum that's similar to Stanford, and you compare a black body emitter to a the ideal selective emitter that I just showed, and you plot that, the temperature reduction that you can get as a function of dew point that measures the water content of the atmosphere. So what you see is that over a large range of dew point, the black body emitter will give you somewhere on the order of 10 to 20 degrees Celsius, which is consistent, reduction from the ambient, which is consistent with the experiment that we have carried out. On the other hand, you can have a much larger temperature reduction, sometimes on the order of 50 to 60 degrees Celsius below ambient, by switching into a black body emitter. So you can actually get extremely cold passively with these kind of structure. So I talk about the importance of using a photonic design in order to improve the emissivity spectrum. In addition, a very important consideration in order to go to ultimate performance is to suppress the parasitic heat leakage that the environment may put on the emitter. And here is a comparison of the black body emitter, which is shown as the solid line, and the selective emitter, which is shown as the dashed line, for different parasitic heat leakage. In a typical parasitic leakage parameter, 8 watt per meter squared per Kelvin, which is what many of the conventional apparatus typically have, the temperature reduction between the black emitter and the selective emitter is actually very, very small. On the other hand, if you can very substantially suppress the parasitic heat leakage, then the difference between the black body and the selective emitter will be extremely substantial. And again, we are talking about potentially at Stanford on the order of minus 50 degree or 50 degrees Celsius reduction from the ambient air temperature theoretically. So with that as a theoretical guidance, we then set out to carry out some experiment. And this is the emitter design that give us a peak in the 8 to 13 micron window and suppress the emissivity elsewhere. And it actually have very broad angular range, which is essential because we want to use as much emission as possible. To cut down the parasitic heat leakage, we adopt a design that look like this. And this is a vacuum chamber. We use vacuum to cut down the convective loss. We use a radiation heat shield to cut down the parasitic back radiation from the surrounding. And we design also all the conductive pathway carefully in order to cut down the conductive heat leakage. So, and this is how the chamber actually look like. So this is the outside view of the chamber, and this is the inside view of the chamber with the selective emitter sitting there. And then we bring it to the roof at night and do our test. So in our preliminary test, we actually get a temperature that's about 27.2 Celsius below ambient air temperature, when the ambient air temperature is around here, is about 15 degrees Celsius. So this is a temperature that's about, in essence, minus 10 degrees Celsius in a summer night at Stanford. So you can really get fairly low temperature here. Now, it will be interesting to put this experimental number in a theoretical perspective. And again, this is the theoretical curve that we draw. These are ideal case of a black emitter and a selective emitter. So our experiment sits here, which actually compare quite well with what you expect from a selective emitter. So we have some parasitic loss, and we're not ideal emitter, so the temperature is slightly higher, but it's roughly speaking on the curve. Now, it will be interesting to compare this with the world record in radiative cooling that was done a long time ago. They were able to get to a temperature reduction of about minus 32 degrees Celsius below ambient. But what they have to do is actually to go up to a particular mountain that has extremely low dew point, and therefore the air is extremely dry. On the other hand, judging from the theoretical curve, what we are already seeing is even without going into the top of the mountain, just in places like here in the densely populated area, there is actually a potential to beat the record in terms of temperature by a significant margin, even with the atmosphere condition that we have here at Stanford. So we think that actually is quite exciting because it proves some of the fundamental physics of radiative cooling, especially in terms of the use of selective emitter. And also, a large temperature gradient can be very interesting for power harvesting purposes, because with temperature gradient, you can harvest power out. And so, and that produces perhaps a possibility of doing nighttime power harvesting with actually substantial energy density or power density if you compare that with what other ambient power harvesting techniques that's available out there. So with that, let me briefly summarize by acknowledging the people who did the work, especially Ashwath Raman, Lin Xiaozhu, and Zhen Chen. And Zhen Chen is the postdoc that has been supported by GCEP in really on the nighttime radiated cooling side. So with that, let me stop and thank you for your attention.
Yes, question over there.
Yes, thank you very much. Very exciting. You mentioned watts only in one slide, and it went by too quickly for me to really absorb it. But I was trying to, all the way you were talking, I was trying to analogize temperature difference in voltage and then throughput, heat flux with current. And what happens when you start to draw heat flux off that temperature difference? How much power can you really harvest?
So I guess in the daytime cooling experiment, I didn't go into detail because I don't have that much time. We measure what's called a cooling power. And because the thing has a temperature lower than the ambient, you can put heat load on it to bring its temperature back to the ambient. That measures what's in the literature called the cooling power. In that experiment, the measured cooling power during the day is on the order of 40 watt per meter square. At night will be a lot larger. I think you may expect somewhere on the order of 80 watt per meter square or something.
That would actually be consistent with some experiments in the Kansai region of Japan using ordinary selective surfaces to cool the high and medium temperature cases in a supermarket, and that worked fine. But it's interesting that even without selective surfaces, I was looking at your graphs, the ancient Shahs of Iran would get sorbet made for them by putting a saucer of water at the bottom of a deep well where it could see only the -40 sky and not the scattered solar radiation. So just the simplest passive actually finds this a very useful resource if you're the Shah.
Right. Oh, absolutely. I think nighttime, you mentioned a very nice example. Nighttime radiated cooling has a very long history. And the typical performance that people get at night is somewhere close to freezing temperature. Our contribution here is to point out that you can do it during the day. The Shah certainly didn't do that. They wish, I guess. And also at night, you can push this much, much further than people have done.
For your PV cooling system, the design works very well for a back contact cell. Have you given any thought to how you would be able to structure this taking advantage of silver on the front?
So I think it would be very interesting. The key challenge is really to make sure that the thermal contact or to reduce the thermal resistance between the front layer and the cell. So certainly I completely agree with you with a back contact cell where if you have an entire front surface to play with, it would be great. But I imagine that you can similarly imagine maybe a conforming surfaces on the front contact cell for cooling purposes as well.
Other questions? So I have a question. So for some of your experiments, you isolate the convection effect. So in the real system, how much convection will contribute to this either heating or cooling compared to radiation?
If you are talking about below ambient, if your objective is reach below ambient air temperature, then you need to very strongly suppress the convective effect. So even in the early experiment, we use a polyethylene film to cut down convection. For some of the cooling where the operation temperature is above ambient, you actually don't care. So the solar cell cooling, for example, you don't need to cut down convective at all. But if the objective is to get below ambient, then that's very important.
Yes, one more question.
So, do you have to face the sky, or you can face anywhere which has the thermal emission which is less than the ambient, or some material in the ambient has less emission?
You need to face something that has a temperature colder than the object that you are trying to cool. So the sky is the most natural one. And I think, in fact, in many situations, if you have a low cloud, for example, the radiative cooling would be significantly affected because the temperature of that cloud is not very low. Okay.
Last question over there. Yeah. There. Yeah.
I was just recently told that there's a desert in India where the temperature gets to 140 degrees, and it's a good place for solar concentrating collectors, but it's really hard to cool things there. I wonder if there's some possible application here.
Absolutely. I think it is actually a very interesting way to think about it, because this thing usually works best at the location where the solar cell also works best, which is where the sky is clear. The sun, of course, comes through, but then the heat can go out. So it's very interesting to look into this combination. We have actually quite a bit of ideas about it.
Due to the time limitation, we'll carry the discussion after the session. And thank Professor Shanhui Fan again for his interesting talk.